During the setup, the first thing we'll be doing is setting up the turbulence model. We will be using a K-Omega SST turbulence model because it is able to accurately capture the pressure gradients. Next is outlining the different boundary conditions which have been allocated in the meshing module. There are many different boundary conditions that can be used, but these are the following that we'll be using for our situation. And then in the Solutions tab, we'll be using the pressure velocity coupling scheme. Now, a segregated solver first solves momentum equations using a guessed pressure and then corrected. Due to the guess and check nature, a large number of iterations are required. Using a coupled solver, which solves pressure and velocity in a single system, reduces the number of iterations required for a convergence to a steady state. The residuals are an indication of the difference between successive iterations. As they converge, the residuals should decrease. We will also be measuring the lift and drag of the fairing. Sometimes we can find that global residuals may oscillate, for instance an issue with one cell, but the monitor points may be stable. We can then initialize and run the solution. When the Fluent dialog box appears, click on Double Precision and then increase the processor to one less core than you have. This computer has 4 cores and will be using 3 processors, where one is left for reading and writing on the disk. You can then check the mesh to report its dimensions and report its quality, and display different name selections. You can also determine if you have forgotten to name a face, as it will come up with a generic name. Under the viscous model, you can start to apply the K-Omega SST turbulence model. As you can see, there are many turbulence models. The theory can be found within the ANSYS help guide. Next is applying the boundary conditions. The name selections will have boundary conditions automatically assigned to them, which can be changed. Now the fairing is a stationary no-slip wall. We have a moving ground at 40 meters per second in the negative Z direction, a 40 meters per second inlet with a 0 gauge pressure outlet. Make sure to highlight the average pressure specification. Now a sky is traveling at the same speed as the ground, so 40 meters per second in the negative Z direction, and the symmetry planes will be automatically registered. The reference values can be updated, leading to accurate CL and CD calculations being displayed during the iterations. And under the method, you can change the scheme to coupled and add lift and drag of the fairing, highlighting plot, and print to console. Initiate and let it run for around 50 iterations. And for a quick check, you can use the Fluent post to make sure the contours look as expected. You can check to make sure that the velocity of the ground and the sky are traveling in the right direction.